right. Yeah, my name is Radi. I'm co-founder and CEO of Irreducible, a company that works on high-performance proof generation. And I'm today going to be talking about an Keccak, which is a custom CPU that we developed at Irreducible. I want to make it crystal clear at the very beginning that we are not talking about a custom ISA for ZK VM. So I'm sorry if someone is disappointed, but this talk is going to be good as well. It's going to talk about different things. It's talking about actual CPU. So again, this has nothing to do with ZK VMs. This is talking about real physical hardware. What I'm going to be talking today, I'm going to give a little bit of a review of evolution of hardware acceleration. I'm also going to be talking about this particular instruction set architecture, which is native to the binary tower fields which are used for Binius, our proof system. I'll talk about the CPU design, I'll talk about our performance results, and I'll reflect on the future work. Just wait one more second, still have people coming in before we get to the good stuff. All right. Let me check if this, okay, this works. So evolution of hardware acceleration. We are in this industry where there is quite a few hardware teams right now who are working on accelerating proof systems, and pretty much until this point in time, hardware acceleration followed pretty standard approach for like our previous work and work of our competitors. And what does this work consist in? It really starts with CPU profiling and bottleneck identification. This is something that we historically saw with MSMs, entities, Merkle trees, etc. These are like usual suspects. We run the profiles on CPU execution, we identify the bottlenecks, and then we try to do so-called hardware offload. Hardware offload means that you take portion of computation and you offload to hardware, and this historically was done using GPUs and FPGAs. And there is quite a few teams out there which are also working on custom silicon ASIC design for the purpose of hardware offload. And then the last thing that you need to do is to do the integration. And I'm just gonna mimic server here, and in typical server you have a CPU, you have a system memory that talks directly through DIMM slots to this server, and then you have notion of motherboard. The black stands here for PCI Express, and then you have several hardware accelerators plugged into PCI slots. These can be GPUs or FPGAs or custom ASIC cards. And you really offload single module to these and try to accelerate as much as you can. Now there are a few challenges, and these are the challenges that we've been hitting in past 2 or so years. First of all, you have to have a high bandwidth in between the CPU and the hardware accelerations on your PCI bus. This requires really low-level sophisticated kernel engineering to be able to do so. Second of all, your hardware modules need to follow the protocol updates. So your hardware team needs to be capable of quick iterating because protocols are changing fast, and that puts really interesting dynamics in between hardware design and hardware software co-design in terms of integration. Development cycle is pretty bad, basically. That's what every hardware team has been talking for the past 2 years. Now, this is an interesting point. I really need to stress this one. There is a massive disbalance in between the system memory, which is right next to the CPU, that basically all the stock proof systems are running in, and the memory inside the hardware modules. We are talking about 1 to 2 terabytes of system RAM, which is sitting right next to the CPU. And we are talking only about 16 to 32 to 80 gigabytes these days, which are sitting on FPGAs and GPUs. What does this mean? This means that you need to find a way to design transactions from the system memory into hardware and process things in time, creating some notion of pipeline. Like you can't just dump your entire trace in hardware and have it all executed. So these were the problems that we typically see with custom accelerators that companies publish in the past 2 years. We were one of them. We have a working example. This is Polygon ZK EVM accelerator. So a typical example of profiling and successful acceleration using this approach. What we have on the right-hand side is a very beefy CPU server found in Google Cloud, which has 224 virtual cores, threads. And basically, this is the profile of execution of the ZK EVM on that machine. It's dominated by Merkle trees, hashing, and by LD, which is really a bunch of entities which are happening during the low degree extension. And Irreducible takes this proof system for acceleration. We run it on our server, which only has 64 threads and virtual cores, and obviously it executes slightly slower when we run CPU only, but then when we apply acceleration and we tackle LDE, which gets shrinker, and then we tackle also Merkle tree in separate hardware accelerator, which completely basically disappears, we get accelerated version. Now this version is 2 times faster than our software model. It's basically 160 and 84 seconds. And this is really proof that traditional approach works. We were able to accelerate quite a few things this way. You can go to our website and find the blog post which provides detailed explanation on Hermes, on Polygon ZK-VM acceleration, but we also have recently achieved acceleration of succinct SP1, and if you haven't passed by our booth, which is on the ground floor, and you can have the profiling numbers for SP1 done in exactly the same fashion. Now, we are the company that actively develops Binius. It's our proof system that we introduced in November last year, and this is first time that we are talking today about actual hardware acceleration of Binius. There's been a lot of discussion about its cryptographic benefits, etc. And obviously, internally, we were challenged to design a really good accelerator for Binius, and this is how Keccak became a thing. So before we go into Keccak design, I will just tell a few advantages of Binius and binary tower fields. So first of all, binary tower fields operate carryless arithmetics, which is really hardware friendly, and there is a recent blog post also found on our website, which claims that binary tower fields, when it comes to hardware, are 5 times more efficient than mercenary one. And I also want to make it crystal clear, we are not comparing this on CPU, on GPU, on any sort of existing hardware. We are comparing this in terms of ASIC design. And our findings are that binary tower fields are 5 times more efficient. Essentially, if you make 2 chips of the same size, you spend same amount of money, you're gonna get 5x more multiplication outside of binary tower fields. That's intuition for this arithmetic efficiency. Second thing is, and this is now where we start talking a little bit cryptography, Binius features reduced tray size. This is really important for us because it's minimizing the memory footprint of the proof system, and this is because in Binius, your elements can be 1-bit, 8-bit, 16, all the way to 128. So unlike prime fields, unlike Plonky 2, Plonky 3, which run on Mersenne or Baby Bear 31, you are not fixing your element size to describe your proof system and ZK-VM or whatever the application is. You have availability to use different field element size. We call this reduction of embedding overheads, and this is really important. Second thing, which is very important about Binius, it brings OG hash functions which run in production for decades so far and are implemented in binary fields. Everybody knows about AES. There is Grostel, which was also finalist for SHA-3. They are all good example, but there is also work that we did Irreducible in introducing a new hash function, which is particularly optimized for binary tower fields, and this is also something that we wrote about previously, Vision M32. Now, when it comes to development, this is where things start to differ from other proof system that we were talking about. So first of all, polynomial commitment scheme is fast. This was the bottleneck for Halo 2, Plonky 2, Plonky 3, like choose your own favorite snark or stark from 2 years ago. PCS was always the bottleneck, either entity plus MSM or entity plus Merkle tree and whatnot, quotient polynomial computation. Here situation is completely different. It's the sum check, which is the new computational challenge. And it's such computational challenge that requires completely new paradigm of computing, and basically the previous approach cannot work. So let me try to explain why the previous approach doesn't work. This is the Binius execution on CPU. Tool that we use is called Perfetto, and Perfetto essentially plots these swimmer lanes of time spent to do different things. So we have trace generation, proof, and verify steps. Proof step is dominated by sum check, actually the zero check version that we are implementing internally. And then we have another step which is not subject of this talk called eval check, and essentially this is what the proving consists of. If you see the green bit, that's basically the biggest time consumer, the biggest offender, is the zero-check computation. Now, I will just also mention that software implementation of Binius is completely open source, and you can go to GitHub and GitLab open source fork, and we are maintaining this up to date, so you can literally reproduce these results anytime you want. For reference, we are running this on pretty beefy server. It's the same one that we use for Polygon ZK VM. It has 2 CPU nodes, 64 cores each, running at 375 gigahertz. It's basically a beast. And this is what it takes to run. This is actually Keccak proving trace presented here. So yes, our goal as a hardware team essentially is to accelerate this step. So let's see what are the requirements. There are quite a few, and I'm going to try to go the way how we progress on the stack of computation. We start from the low-level side where we have basic arithmetics, and first thing is that here we are dealing with different elements all the way from 1 bit to 128 bits. Why? Then this is instantly tricky for making like custom hardware module which does one thing and one thing only. There is essentially need to support different sizes. Second thing is that we are supporting heterogeneous trace matrix evaluations with some check and zero check. This again creates the problem, right? In certain ZK VMs or ZK EVMs that we saw before, column size is fixed, or there are certain rules how this computation goes, but here we really need to support heterogeneous size, so this is another tricky requirement for our task. Data types. So Binius is an interesting system because if you have a byte in memory, it could be 1 element of 8 bits, or it could be 8 elements on 1 bit. And this keeps changing all day long the way you are progressing through the computation. So this, again, introduces another hardware challenge. Programmability. This is where we try to stay at the same development pace as open source contributions to the software model. So essentially, we can't have hardware solution which is too slow to pick up the latest algorithmic change. So essentially, we need to have a notion of programmability without high overhead. And last, but very important one, is the notion of compiler. Essentially, polynomial constraints cannot be baked into hardware algorithm, like this was the case in certain Stark before. They are not known ahead of time, and they are runtime changeable. So basically, we need to have a way to figure out dependencies and how data looks like at the moment of execution. Coming to a really interesting point that if you have these requirements, you have no other level of freedom but to design a proper CPU. And that's exactly what we had to do at Irreducible. Let's go a little bit into instruction set architecture. First of all, there are 3 groups of instructions organized by ALU, and everything is bitwise because that's just how binary fields and binary tower fields work in general. Then there are instructions associated to the data movement, and obviously a lot of different flavors of multiplication, and proof generation in general is really just proxy for very large number of multiplications. So we had to be good at these, and I'm going to explain some of the exotics which you can find in this CPU and no other CPU out there. Before I get into that, I'll just say that we have 32 register bank. Each register is 128 bits because that's the maximum element size in Binius. So this is really informed from software/cryptography side. Our instructions are 256 bitwise so that they can support 2 operands or 1 operand plus immediate value. We feature SIMD executions, parallel executions, obviously, and it's all very low latency. So we are able to perform large multiplications together with load store operations in 3 clock cycle, which also helps compiler work better. On the right-hand side is the register bank, and what's interesting here, we enable several ways to address registers. Obviously, you can access single register from the compiler standpoint, but you can also address the entire range of registers and also at different offsets. This is very standard these days in like AI acceleration cores and advanced CPUs, but basically you give this freedom to capture the whole set of registers in like one shot and execute operation on it. Let's go into exotic stuff. Bit collect instruction is The signature is provided here. There is destination register, immediate value, and there is pseudocode which describe what it does. But I will try to explain it using the picture here. So imagine that you have 8 registers, each storing 128 bits values, and you actually want to take a 16-bit slice from each register, and you want to dump all 128 bits into destination register. This is a type of instruction that you really never find in any standard CPU out there, but this actually makes a whole ton of sense for proving and the type of computation that Binius does. Because again, this may be a 16-bit field element coming in row major order, and you want to pick them up from the same offset and dump into register and perform computation, which is, for instance, in column major order. So this is really how the cryptographic computation informs decisions of instructions in the CPU. Another interesting example is the transpose function. We do tons of transpose when you start breaking down entities, FFTs basically. Operation, again, pseudocode is provided. I'll just say that we feature 16 by 16, 8 by 8, 4 by 4, and 2 by 2, but really think about this as register bank holding data, and then you have a single cycle operation that you can transpose the content of the registers. Again, there is no like generic CPU which is going to do anything like this, let alone in a single cycle, but this is something that we really need in order to be fast in computing these cryptographic operations. Multiplication is a very interesting one. We do tons of multiplications. We have super fast multiplier that does large field element multiplications, but what happens in Binius, and I don't think it happens in other proof systems, is that you are multiplying, say, small field element with a large field element. And this can be very exotic. You can take 8-bit value, multiply it by 128-bit value, and then your result is again 128 bits. And now how you support all of these combinations that can happen without wasting too much hardware. So we came with pretty interesting concept of mixed multiplication, and it works in the vectorized style. So pseudocode that I'm executing here is really just multiplying two 32-bit values and writing the 32-bit result. So from register perspective, I'm picking up 32 bits here and 32 bits here out of 128. There is network of Karatsubas. There is 9 8-bit registers, 8-bit multipliers, then another layers of Karatsuba, and you are able to provide result. In this particular example, when your operands are 32-bit each, you actually end up using all 9 quote-unquote small multipliers which work in 8-bit resolution and get the result. But now this is very interesting. You have the same hardware, so actual same silicon, quote-unquote, all logic gates, but this time you are doing 8 bits times 32 bits. So in software, you know, like if you are doing this on GPU or whatever, you actually need to go probably through different pipelines and registers, but here we try to recycle, reuse the same hardware. And again, example, we are taking 2 8-bit operands from the same register, 32-bit value, but then left-hand side 8 bits only propagates through this circuit, and right-hand side 8 bits, they only propagate through this circuit. This time utilizing 4 multipliers each. M4 is not really used in this case, but what this gives us 2 results in parallel on the same clock cycle. This is another example of very exotic approach to multiplication, which is informed by cryptographic properties and how we can mix and match small or large fields. This wasn't just theoretical study or simulation or emulation of a design. We went ahead and implemented the actual CPU. Now, I will make it also crystal clear, we didn't tape out custom silicon. We prototyped this on our FPGAs, and I'm going to share the findings of the design and the performance result that follow. So we were able to prototype 48 cores CPU on single FPGA card, and a little bit of system information. There is a bus which runs at 250 megahertz clock, and there is basically PCI controller to talk to the motherboard and the host. And what's on the picture is like the grid of 48 cores, where core 0 is highlighted, and the CPU here implements the instructions that I was talking about, and it has associated data and instruction memory right next to it. So this was implemented on the board. What you're looking at is the actual FPGA layout. So this is what logic looks like when you look at the implemented multi-core CPU design. The yellow portion at the bottom is on-chip memory. This is pretty big 16 gigabytes memory inside the FPGA, which we use for data and instruction storing. The orange color is the PCI controller that talks with the motherboard and the host, and then everything else is the logic, which carries 48 of these cores in a multi-core CPU. So we implemented this internally, tested, and basically I will also share a little bit about software implementation. So this CPU requires its own compiler, right? So you can't plug LLVM or any other solution out there because instructions are very tricky, and generally speaking, when you don't have instructions such as branching or jumps, stuff like that, these architectures are typically known as DPU, like data processing unit. You kind of want to have a symbolic way to describe the code. And since we are obviously working in cryptographic field, it's really cool if you can describe your Keccak function really through the polynomials and then have it compiled to actual instructions which are operating on the CPU. And this assembly here shows you ALU, load pipeline, store pipeline and load pipeline and how they look in the time domain. You will see very interesting things that you have read from memory and store from memory in the same clock cycle because we are featuring true dual port memories. We actually support this case efficiently. And then if you look the computation side, you will see a lot of multiplications and additions back to back. So this is really the output of compiler, which was written symbolically. And these are the instructions that get executed on this multi-core CPU. Interesting part, performance results, like why we are doing all of this effort. We are seeing pretty significant performance improvement. This is, again, Keccak example that I had Perfetto trace, and on the next slide, you will get the visual digest of this table, but what I really want to stress is this is the CPU-only execution of Keccak proving, and this is the accelerated version. If you compare the total time to compute some check, we see roughly 5x speed improvement, but for some of the earlier stages, which are very slow, we actually see like 7 times speed improvement. And this is really like why hardware should exist in this industry. It's not really to try to shave off 20, 30% of your performance. It's really to get you 5, 10, 20, 100x over the reference software module and make it worthwhile. If we go back to proofs, to Perfettos, sorry, on the upper one is the CPU only. This is exactly the same one that I presented many slides ago. This is the round 0, 1, 2, 3, 4, etc. of Keccak proving, and this is what it looks like with hardware acceleration. So round 0 corresponds to this one, 7x improvement. Round 1 corresponds to this one, more like 5 to 6 times improvement, etc., etc. Future work, this is really just the first cut of the CPU that we made, and we're able to successfully prototype. There is plenty of improvements that we can do across the stack. So as we spoke about requirements in different stages of the computation, I'll also talk about future work. So yeah, we are looking to add a lot of more vectorized instructions and increase the compute density per core. We are also trying to fit the entire trace into on-chip memory so that we can completely eliminate, well, not completely, but significantly eliminate communication to CPU and back. So essentially, we want to hold the whole trace in on-chip memory. And yes, we just need to try to get basically more cores on a single FPGA and running at higher frequency. So, you just take this one. If we can make it run on 500 megahertz, we have currently designed running at 250 megahertz, that gets you 2x out of box, and we take it from there. So yes, there is really a lot of room for improvement. And our servers support many FPGAs in the same chassis. We can fit up to 8. So we think that we can distribute some other portions of the proving on more FPGAs. The function that I call eval check that you saw before, we didn't even touch this yet. So we are only focusing on some check and zero check, and definitely there is a lot of room for improvement there. Compiler is a big one. There is always identification of new instructions, sorry, like exotic ones that are not obvious, and basically adding new instructions could really improve the performance, and we need better support for software for vectorized computation. Having said that, thank you so much for your attention, and please check out our Twitter and website. If you see anybody from Irreducible, they're having these stickers, which are our open roles. We are hiring across the team, and yeah, if you are interested to be part of this journey, please let us know. Thank you.
Thank you. Thank you, Radi. We have a few minutes for questions, so time for Q&A. Any questions from the audience? Okay.
Why does the performance difference flatten in the later round? So in the first you have this increase, and in the later it's almost the same.
Yeah, that's a good question. So the way SumCheck works, there is part that you're doing first, and there is also folding component, and not everything is as efficient. So in these rounds, you do less folding. In these rounds, you do more folding, and the more folding you progress in the later stage, we get, relatively speaking, less efficient. But yeah, this is something that we want to try to tackle by adding new instructions, which are tackling exactly this type of computation.
Yeah, so you're simulating a hypothetical CPU architecture on an FPGA, right?
Yep.
What would be the performance difference if you just directly encoded like the computation doing in the FPGA instead of like first simulating the CPU architecture and then doing it through that?
So am I getting this right? You're basically saying, what if I don't do CPU on an FPGA, but I actually make a custom image for FPGA that is just tackling Keccak, for example?
Yeah.
Yeah, we could do that, and it would be probably similar speed, but then you have this problem that for Keccak you need to have kind of custom images, but then it's not that our prover is only proving Keccak all day long. Like then you have the problem that if the next one is, I don't know, Lasso or GKR or whatever, you know, the proving task is, then you need to do a different circuit, and that FPGA which is only doing Keccak becomes pretty much useless. So that was one of the reasons that we have to change the paradigm and get into CPU architectures, which, you know, just run on FPGAs, like because we can and because we are not yet building ASIC, even though we plan to have eventually custom silicon doing all of this. But yeah, this justifies the call for CPU approach and not like hardened image that does only one thing.
I see. Thanks.
Sorry, kind of a follow-up question. I'm no expert on FPGA, but what will be the performance difference if you implement this CPU on silicon, actually?
Yeah, I was hoping somebody would ask. So basically, this is kind of the name of the game. So the system clock here, we are pretty much limited at 250 megahertz. We can do at least 1.25 gigahertz, so you get 5x immediately just by faster clock. Second thing is, how many of these cores you can fit? That becomes the question of like how big chip you want to make, depends on power budget, cooling, etc. But I feel like that you can get at least 5x on the clock and probably another 10x in terms of just efficiency. So it can be 50 to 100 times faster if you have a custom silicon for this.
Do you have plans to do that?
Yes, we are definitely planning to make custom silicon for Binius proving and for binary tower fields. Like we feel very confident, given all the research that we did, that binary tower fields are the future of verifiable computing. And also our research shows that GPUs or CPUs are not really as good for this type of circuit. So yes, we definitely are planning to have a custom silicon for this, obviously keeping all the programmability and compilers and software support for it, but it's subject to, you know, ecosystem maturity and demand for proving.
Thank you.
Thanks.
Great. Thank you very much.
Thank you so much.
Thanks.